Alright, so I am going to try and get you through day 3 notes. So they aren't too long. This video shouldn't be too long unless I slow down, I guess. Alright, starting off, remember your homework is going to be number 11 tonight, even though you took your test today. This is a result of our snow day. So day 3, here we go. I'm going to start you off here. So fundamental theorem of calculus part 2 was where the integral from a to b of f of x dx was f of b minus f of a. So just so that we're clear of what I just said, Ftc2 was this piece, how you evaluate your definite integrals. So now we're going to learn part 1. So part 1 is kind of interesting. I'm going to start you off with a little mini lesson where we're going to shade some area. So the first guy right here, you'll notice there's no value up top. It's an x. So what I'm going to do is just look at the fact that it says the function of x, but then the integral says t and dt. So what I'm going to do is I want x to be number 1, or x to equal 1. So for this first guy, the integral notation, which I should have another space there, but I don't, would be from 0 to 1 of 2t plus 1 dt. So that would be this area. And then this one would be from 0 to 3 of 2t plus 1 dt. And this last one here, obviously you kind of get my point, is the area from 0 to 5, 2t plus 1 dt. So I understand that there's t's, but the x that we were using, I've now gone through and identified pretty much what f of 5 would be, based on the original definition I had up here. It would be the net signed area. And the fact that graphically, this graph shows what the area would be. When I evaluate and I find my antiderivative, even though there's t's, I'm just going to substitute in those values of 0 and 5. You end up with a value when you're all done. So the integral actually depends upon that x that's up top, which is why we have the function written as f of x. So I'm going to start you off by doing this problem. And you're going to ignore the dx. We're going to find the value of this integral first. So to start off, I would need my antiderivative because I'm using Ftc2, t squared plus t. I would need to put in my x value, or my b value, which would become x squared plus x, my a value, which is 0, and then my actual antiderivative, my integral, would just be this, right? So I did the inside of my brackets, so now I'm rewriting the problem. X squared plus x. And I end up with, taking the derivative of that with respect to x, I get 2x plus 1. Looks very similar to what we started with, only now I have x's in there. Let's look at the second one. Same thing. This piece of it, antiderivative, I won't even put x there. I'm just going to write f equals. Antiderivative would have been t squared plus t. F of x is x squared plus x like before. F of 3 would be 9 plus 3 more, which is 12. And so I end up with the derivative of x squared plus x and then minus that 12. Well, that gives me 2x plus 1. Looks very similar to what's here again. And hopefully you get my drift. We already got the antiderivative here, and we have f of x, so I'm just going to find f of negative 2. F of negative 2 would be 4 minus 2, which is 2. So I'm going to rewrite my problem. The derivative of f of x, or f of b, which would be the x squared plus x. Remember, I'm skipping this step because we already have the answer sitting right there. And then minus the f of a value. Taking the derivative of that, I still end up with 2x plus 1 because the derivative of a constant is nothing. So you start to see a pattern here. And that pattern gets you to the fundamental theorem of calculus part 1. it says that if there is some function that I am taking the integral, and it has to be a variable or a function, and this here has to be a constant. And the constant must be the lower limit. So if it's the upper limit, you're going to have to use the negative rule to flip it. So this says that if I take the derivative of an integral from a constant to a function of another function, you're, in a sense, canceling the derivative with the integral, and you're replacing the t with an x. So it might look kind of complicated, especially with all those lines everywhere. But in using the rule, I have a constant, I have an x, I'm taking the derivative of an integral, which means you're going to take this x value and put it in for t. And that is the answer. You don't need to take the antiderivative. You don't need to take, you pretty much don't need to do anything. But I am going to prove that. So number one, let's start off with the antiderivative of cosine, which would be sine. F of x would be sine of x. F of negative pi over 2 would be the sine of negative pi over 2, which gives us negative 1. So I'm going to rewrite this problem as d dx of f of x minus f of negative pi over 2. But that just gives us cosine of x again. All right? Number 2, I'm actually going to do the work again, and then after that we'll skip down to the other two without using the rule. So antiderivative, whose antiderivative is that? That's tan inverse of t. F of x would be tan inverse of x, and then f of 0 would be the tan inverse of 0. So the tan inverse of 0, remember, I need an angle whose tangent value gives you 0, and the angle is 0. So therefore, if I want to take the derivative of f of x minus 0 equals, see, 1 over 1 plus x, or u squared, times du dx, in this case would be 1. So right back to the original. So I'm not going to make you do that every single time. I would want you to recognize constant, variable, derivative of the integral equals. So you're replacing that t. In this case, you'll notice that the constant is not where it should be, so we're going to have to take the derivative of the negative integral of 3 to x of 1 over t plus 1 dt. And that one, we're going to end up with the negative derivative of this guy would end up being 1 over x plus 1. And that is the answer. So, using the chain rule, we're going to actually do that first one real quick. So, notice it's not just x anymore. That's the difference here. So, antiderivative was sine of t. F of x squared would be sine of x squared. F of 1 would be the sine of 1. I use that just so you understand. You don't know what that value is. The sine of 1 is an angle in the first quadrant, but pi over 2 is about 1.57, so the sine of 1 is somewhere in there. We don't know the exact value. So for this problem, we are going to change it to the derivative of f of b minus f of a. So sine of x squared minus sine of 1. And in a different color here, I'll do it in red. The derivative of sine of x squared, that is a chain rule. Derivative of the outside, leave the inside alone, times the derivative of the inside, and then the minus sine of 1, that's a constant. So there is my answer, which looks a little bit different. Now, if I tried to use the rule we were using before, this part would make sense, cosine of x squared, but that 2x shows up. So let's try one more. Let's do this guy right here. So antiderivative would be x cubed minus 2x squared plus x. f of 3x would be, and I'm not going to simplify, I'm going to leave it this way, and I'm just going to do chain rules to it. And then plus, oopsie, 3x. And then f of negative 2. So f of negative 2 would be negative 8 minus 8 minus 2, so negative 18. So, running out of space here, but I do want to finish this off. I end up with, and let's do up top, the derivative of f of b minus 2 times 3x squared plus 3x minus negative 18, so plus 18. All right, so see what we end up with this guy. Sorry, guys, running out of space. So, derivative of the outside, oopsie, leave the inside alone, derivative of the inside, minus derivative of the outside, leave the inside alone, derivative of the inside, plus 3. So what you will notice is this whole thing pretty much looks like everybody has an extra 3, and I have a 3x squared minus 4 times 3x, and then I have a plus, whoopsie, did I make a little mistake here? I feel like no I don't, plus 1, perfect. So, other than this little extra guy right here, the rest of this looks like 3x squared, 4 times 3x, exactly the same function that was already there. So hopefully you kind of see the pattern. And if you don't see the pattern, I'm going to do the pattern for you now. So I'm going to erase the board so that I have some space. The pattern is, let's take one right here. So first thing we're going to do, we're going to have to flip this guy. Derivative of negative integral of 2 to 4x of 5x squared plus 6 d. Actually, to be honest, that should be a t and that should be a t, and I make that mistake a lot. That should be a t, that should be a t, and that should be a t, and that should be a t. All right, so dt. So if you are taking the derivative of an integral where you have a constant in the lower limit and a function in the other upper limit, we're first going to substitute in for all your x's. In this case, I only have one x. So that would be 4x whole thing squared plus 6. And then the key is the fact that you have to multiply by its derivative, 4. So I'm going to go back to the problem we did right here, and let's take a look at it. So that 3x would be going here and here. So we get 3 times 3x squared minus 4 times 3x and then plus 1. And then remember, multiply the whole thing by the derivative of 3x, which is 3. And that is exactly what we had a second ago. Letter D is a little interesting, and it always takes me a second to explain, so I'm going to do that on the next page. The fundamental theorem of calculus is right here. With the chain rule, I want you to go back to your notes where the original rule was, and I want to do it with the chain rule, and I want you to remember it with the chain rule instead of the original. You're going to find that if you want to take the derivative of an integral from a constant value to a function, and we're going to call that function u of x. So some function of x, of f of t dt, then that is equal to f of, so wherever you see an x, we're going to replace it with that function, or t, and then we're going to multiply it by du dx. That is actually the rule. So here was my du dx, here was my du dx. So, letter D. Let's take that problem, 5t squared plus 6. So, let's go over. Whoopsie. Derivative of the integral from x to 2x 5t squared plus 6 dt. So hopefully that's the exact same problem, and yes it is. All right, so the issue with this, that's not a constant. So here's what we're going to do. We're going to use the rule that the integral from a to b of a function plus the integral from b to c of a function equals the integral from a to c of that function. So here's what you're going to do. You're going to pick any number. Doesn't matter what the number is. And you're going to break up this integral. So what I'm going to do is I'm going to write my derivative back, and I'm going to break up my integral. I'm going to make my integral start at x, and I'm going to go to some value. Okay, you can pick a number. In this case, I'm just going to pick a as my number. It's a constant. If you want to pick 8, put an 8 right there. Okay, and then plus the integral from a to 2x. Now, it actually does not matter at all what value you pick there. So if you want this to be 8, then write an 8. You want that value to be -4, write a -4. It does not matter at all. So once you have that, and you know that these a's are constant numbers, this one is set up properly, and this guy is not. So what we're going to do, I'm going to move this up so I can do it. We're going to flip. So this one we'd have to flip. The constant's now at the bottom. My variable or my function is my upper limit. And then this one we can leave alone because the constant's still on the bottom. There's my upper limit. So my answer becomes, I'm going to substitute this in, negative parentheses 5x squared plus 6. That's the first integral. My second integral would be plus 2x, whole thing squared, plus 6. And then I'm going to have to multiply by the derivative of 2x. I'm going to squeeze that in front here, times 2. And yes, you should simplify that in this case just because it's notes for you guys. I'm going to leave it at that to save a little time for you. And then here is a easy multiple choice question. So the derivative of an integral starting from 2, constant, until a variable, would be square root of 1 plus that squared. And then I'm actually going to put times the derivative of x. So this is the derivative of x, which was this top guy. Okay, I'm doing that so you get used to making sure you multiply by that, because there's a very good chance that you won't, and you'll get your problem wrong, and these are extremely easy problems. So you have some homework, you have some free response questions, and let me take a look. So I actually wanted to pull up your homework because I couldn't remember which free response questions I gave you. But the way that these questions show up in your free response questions is they may give you a statement that says let g of x equal the integral from, say, 0 to x of f of t dt. If you see this statement in your homework, and I can't remember if I gave you one tonight to do, your free response questions, if you see this statement, you're literally going to take the derivative of both sides. So I'm going to take the derivative on this side, and I'm going to take the derivative on this side. Okay? So when you do that, the derivative of g of x gives you g prime. The derivative of this just gives you f of x, and I can almost guarantee 100% there's probably a graph somewhere to the right that says that it's either f of t or f of x. It's because now you're going to replace that name with the derivative graph. So the questions are going to be pretty much very similar to what you're used to, which is a derivative graph, and then they ask you questions about the function itself. So for this type of problem, you'll see that when you read parts A, B, C, D, they're not going to ask you about function f, they're going to ask you about function g. Where is g increasing? Where does g have a point of inflection? So they actually become pretty easy questions. So I can't remember if that's tonight, but if it's not tonight, then we'll discuss that tomorrow in class. All right, there you go.